Hello and welcome to lecture 5. Today we're talking about collections. What do I mean by collections? That is, how do we have multiple components and handle that in a nice programmatic way? This is a fun lecture because up to this point in the first 4 lectures, we've covered chisel to the point of being able to do what you can do in Verilog. We covered, hello world. We covered combination logic. We just covered sequential logic, doing things with state and registers. So now you can build anything you can do in structural Verilog, right? You can build combination logic and use registers, put them all together. Cool. But what's the advantage? The advantage is from here forward, right? What can we do that's kind of fun and more higher level? And so one way to get at that is collections, right? In other words, I have a hardware component where the amount of things inside there depends on the parameter from generation, right? It's not just always the same thing. I give a generator parameter, that's going to change the number of things internally. So in order to structure that code, we're going to use collections. So collections, of course, come from Scala, and we're going to be using those to build up these more intelligent hardware. So fire up some headers, sure. Cool. Good to go. So, what is the most common collection used in Scala? Something called a seq, which is short for sequence. Um, and so, what is it? You can think of it kind of like a vector, right? It's a collection of things. Um, there's a notion, sequence, there's a notion of order, right? There's something at index 0, something at index 1, something at index 2. By default, the seq is immutable, right? So, in other words, the size of the sequence is set, the contents are set. It's just a collection of things. Great. And so you can see like down below, I declared one called L. I give it initial values 1, 2, and 3 at the time I created it. I can index into them, sure. So in zero-based indexing, so index one, of course, is the 2. I can call methods on it like is empty or non-empty. This is yet another example of what Chisel likes to do in their design of things, where not only to have a lot of methods, they want to make things really clear. So you can imagine having a dot is empty, and then up to the programmer to put a not sign in front of it and say not dot is empty. Someone Chisel thought, or someone in Scala decided, you know what? Let's have more names for things. And so, yeah, there's a lot of nice idioms and things in the language that kind of make your code more clear, more readable. We can call things like course like dot length, sure. Now, these other things are a little bit more verbose, right? So, for example, what about dot fill? So, fill is going to give me 3 elements of this next thing. So then it gets 3/8. Now, the syntax may be new to some of you, where you notice how there's 2 sets of parentheses here. There are reasons why for functional programming, which we'll cover later in this quarter, having your arguments arranged in this way is beneficial in some cases. For now, you can treat it as boilerplate. But the key point is, yes, this .fill actually takes 2 sets of arguments and 2 sets of parentheses. Now, if I had left this off, I'm going to get interesting partial results. I was actually not going to even get a partial result, so say I need to fill it out. So, oops. And I just killed it. Note to self. Oh, no, I didn't. Okay, great. But I killed something. Okay. Well, here we go. As always, I'm due for about 1 or 2 notebook freakouts per session. Great. Well, not that broken. Yes, question. So fill is the first number there is how many elements it is. So it's not so much what index, it's more just that, like, I had 3 before, now I have 5. And so the reason why I showed you dot fill, it's a very specific, Scala thing, is you can see in hardware this is very common, right? I want to have, n registers. Well, I should use dot fill on a register to get n registers or something. Um, Once again, you may be wondering about all these different methods. How do you go about navigating all these, right? Uh, there is Scala doc, right? There's API documentation, so you can scroll through and see all the zillions of methods available on the seq. There's a lot. Um, More generally, uh, a seq or a sequence is a collection provided by Scala. And talk to people who write a lot of Scala, they actually argue that the collection of all these different types of collections in the library is actually a string for the language. So a lot of things we think might be language features are actually library features, and the selection library is really spiffy. There's a lot of data structures for various things you would need, and they're all there and they're really helpful. More generally, if you want to see the entire collections library, you can see that there's a whole class hierarchy. We'll come back to this later in the quarter when we talk about object-oriented inheritance. There's also mutable variants, but for now, we're living in the val world where everything's mutable. Sorry, everything's immutable, excuse me, and that's that. Now, one thing I want you to be aware of when you come across this, for this course and in general, you can just always use the word seek, and that'll be fine. technically, uh, that's one of these, higher level classes now to oriented inheritance. When it actually gets turned in the code, it's going to get turned into one of these base classes of either, list or vector. So you may see list or vector elsewhere in your code. Understand those are castable to seek. And so if you just use seek always, you're fine. The way I've done it in this course, I find for immutable collections, we just always use seek. And it's really clear to everybody in the course, you'll also never mean. There are really subtle performance differences between, list versus vector. You of course can imagine one's a linked list, one's a contiguous vector. Those performance differences will not matter for this course, right? You're not going to have 10 million elements in your seek. So it's not going to matter. So just use seek everywhere. It's clear. Cool. Other questions? Yes, that's a great question. So if I have a seek of chisel items, what is that? So that's going to be those n chisel items, and the seek is the Scala references pointing to them. Now, your question you may be also be asking is there a chisel native collection? The answer is yes, it's called a vec, and we'll get to that later in this lecture, but not on this day. Okay, so then touch more Scala before we can kind of go fully into this. In Scala, there's this shorthand for ranges. You may have seen similar things in Python, where if you say just a number and then until, you actually get the range. So from zero through until four. So until is exclusive, so it's going to be 0, 1, 2, 3. If you use the word two, it's inclusive. So it's also going to be 0, 1, 2, 3. If I made this the same, of course, it would be one longer. Um, Likewise, you can, of course, change the amount increment by. By default, it's by one. You can go by two. You can even go down with -1. So the reason why I have this small slide covering ranges, just because in a second you're going to see me using them. This is why now I can understand that syntax. Okay, so let's do some for loops. So virtually every programming language has a for. The for in Scala is doing a lot of really heavy lifting. It's inherited from Java, so it has kind of very iterative C style, if you want to do it that way. We never ever do it that way in this course, so don't worry about that. The way we do use it is kind of more of this iterator style, like maybe you've seen in Python, where you have, some sort of collection or range, and then you have an element of that, right? So in this case, we're saying, hey, for this iteration range from 0 until 4, give me I, and then I go ahead and print the value of I. Cool, right? You can do some Python, I'm sure that works great. Now, one thing that may come up is you say, wait a second, I have some sort of code, and actually I do want to know what the last valid iteration was or something, right? So maybe for that scenario, you would use a var to track the last value, for example, hypothetically, right? Also works fine. You can use a var. I try to avoid vars, but sometimes the for loops, depending on set things up, there's a reason why that's useful. Um, Now, how sophisticated are for loops? Really sophisticated. You can use all sorts of arbitrary generation syntaxes and do for comprehensions. So in this case, what do I have going on? Even though I wrote the word for once, this actually is two nested for loops with a filter applied with if statement. And so what we get out of here is we're putting these pairs. So in other words, I'm having I go from 0 until 4, so 0, 1, 2, 3. J going whatever value I is until 4. And then I'm only printing it when the condition is satisfied, right? So this is filter applied. I can, of course, remove that filter. And then it's these nested loops. That makes kind of sense. It's triangular, right? If I was to remove that I, of course, it's all 16 of them. So you can kind of see how you can kind of very powerfully play around with this stuff. If you're a person who loves this kind of for comprehension stuff, guess what? Uh, that's there in Scala. So you can go ahead to that page. All sorts of examples. One thing I'll point out now, so we're all on the same page. In this course, we're using Scala 2, so it's going to be slightly different. The Scala developers know that Scala 3 is not widespread use, so the documentation is usually pretty good about telling you what's Scala 2 versus Scala 3. Cool. Other questions? Okay, so we have for loops, we have ranges. What do we do? put to work and build some hardware. So let's build an actual generator. And this generator is something that's getting a little bit more interesting. So this generator is something we call a delay line, or we maybe think of it as a shift register, right? In other words, it's n registers in sequence. So that way, IO.in comes in, and then n cycles later it comes out, IO.out, right? So of course we have, delay n cycles. So we have n is this, delay amount. So how could we go about writing that? Well, first I need those n registers. So let's go ahead and use that seek operation. So here we use the dot fill to get n of them, right? And we're just going to have these, registers. So from the questions from earlier, yes, I can have a collection. This is a Scala collection, a seek, that internally is a bunch of these, chisel objects. And now we have a way to access them, right? A way to kind of point and refer to them. So you can see kind of the chisel and the Scala often kind of intertwine very often inside your code. This is what's happening. In terms of connecting them up, what do we do? Well, we're going to connect the input to reg 0. That's, right here. And that's going to be the first thing over here. From reg 1 until n, so exclusive, we're just going to subtract 1, right? So, from 1, connect to 0, 2, connect to 1, etc. Connect all these other things up. And then at the very end, we're going to connect the last one to IO.out. So this works. If we go ahead and, generate some Verilog, if we say we want to delay by 2 cycles, we can see those 2 registers. We can kind of see them cascading in the way they feed through this design. Technically, register 1, is up here. That's legal Verilog. But it's the generator. This is pretty cool, right? I can go ahead and say I want 4. No problem. This is a pretty spiffy little bit of chisel, and now we're starting to get generation. A System Verilog Pro will point out there's something called a genvar, and you can probably do this case with a genvar. Probably could. We're warming up. We're warming up. We're going to get better. But this is a starting point, right? You can see all of a sudden this is a generator. It's no longer just a single static module. This is a generator. Given what parameter it has, it's going to change the nature of the hardware. It's actually changing the structure, right? You can see based on this n parameter, it's going to change how big this collection is and how many times this for loop runs, right? It's actually like, it makes you kind of more conscious of the fact that we're not just have a hardware design, we have a program that's kind of programmatically building up that hardware design. This is a generator concept in practice. Now you may notice I'm using this require statement. Second, assert. That's there to keep myself from hurting myself. So if I say, hey, give me n cycles, 0 cycles, and it's like, yeah, I can't do 0 cycles, right? And the reason why is you can imagine this code, the way it's written, if 0 comes in here and we have -1, what is that? It's going to break stuff. But yeah, 1 cycle is just fine with this way it's written. You get one register, sure, 10, sure, right? It's a pretty cool little generator. Questions? So this is our, V0. We have a for loop, seek, no use of var. So there's a lot to like. This is very functional code. But let's say you're the kind of person, you know what? I want this to handle 0 cycles. How can I change this? Well, what if you're bringing in var? Which I tell you to be careful with. This is one of those cases where maybe it makes life a little easier. So what happens? Well, sometimes with a careful use of var, we can make it a little bit easier. So I say, you know what? Let's keep this last connection. And set initially to whatever io.in is. Okay. Then I'm going to iterate through all the elements. And notice I don't even bother making a seek. This is a for loop where what does it do? It keeps taking the last connection and attaching a register to it. So whatever the last register was, wrap that in the register, pass it on. Wrap in the register, pass it on. So remember what this is doing. This is a reference to a chisel component, right? This gets passed in as the input to a register, and then the output of the register is now associated with this reference. And so we kind of keep taking the last value, wrap register, wrap register. This is going to work. So I can go ahead and print this out. This will look very similar to the prior one. The name is a little different, but it's the same structure. But notice how now I can actually have a 0 cycle delay and there's no registers at all. And does the right thing. So I don't have to have the require statement anymore. It still works. That's pretty cool, right? So now you can imagine, depending on how you think about things, which one you find more clear. Maybe you find the prior slide with the seek more clear. It kind of makes it very upfront that, hey, I'm declaring, n registers. Now I'm going to wire them up. This one is kind of instantiating one register at a time and wiring it one at a time. This one also uses the var, which, as I said, have some caution with. But in terms of functionality from the outside, this one's a touch nicer because it has a wider parameter range. It can handle a zero. Um, cool. Questions? Do I have another variant? Maybe not. Oh, yes. One more thing. So, uh, let's say I have some combinational logic, right? In this case, I have a three input logic function, takes A, B, and C, has some output. There's some sort of cleverness to that logic. And guess what? Running a tester, I showed you earlier in this today, I promised, hey, you know what? Writing one test case at a time is really tedious. Couldn't we be more clever? Yes, yes, we can. So this code on the right is going to exhaustively test every possible input combination. So how are we doing that? Well, it's three nested for loops, right? For all possible values of A, we're going to try all possible values of C and all possible values of B and C, sure. They're iterating because these are bools. They're iterating between true and false, okay. Technically, these are Scala booleans at this point, and they get cast to bools inside the poke statement dot here. You can see this, right? Okay, so this is going to have, three nested loops, each with two possible values. So it's going to run 2 to 3 times. Set the values. Now, one thing that comes up with these kind of test cases, not only you set the inputs, but you also somehow need to know what the right output is, right? So in this particular test case, I'm doing this expected line where I note the logic should be, I'm kind of secretly rewriting it in Scala, and then I'm casting that to the right type for the chisel interaction. Now, that works for this. If you were critical, you'd say, hey, wait a second, like that looks like almost the same code between here and here, right? What kind of robustness am I getting with this test case? The answer is not a lot. But if the two codes are so similar, what are you getting? But you'll see as we go through this quarter, we'll have more sophisticated ones. There's more diverse ways in playing expected value, and that way you actually get some differences. But for today, the point of this example is to kind of show, hey, we just covered for loops. Let's use for loops to make test cases more general, right? Oops, I gotta first instantiate that on the left, run on the right, and it works. And so in case you were unsure about how something goes through design space, yes, it's iterating between all these combinations. That's a Scala print line here. Now let's say you wanted, instead of the Scala print line, you wanted the chisel printf of what it's working with. And then you ran this and you're like, wait, I didn't get very much. What happened? Well, remember, the print statement in chisel, the printf, only runs once per cycle, right? So I actually need to now start advancing each test case by one cycle. And if I do that, then all of a sudden I'll start seeing, the full gamut, right? I'll see, okay, yeah, for A, B, and C, the way it's set up is kind of printf over here. What are the inputs? What is the output? And overall, the whole test case passes. But yeah, now you know better. Now you know how to do for loops rather than just writing tons and tons of copy paste. Cool. Other questions? I think that's our pause point for today. Yes, it is. Perfect.